In this lecture we discuss about 7-segment interfacing problem. 7-segment interfacing. Using 8255 IC chip, peripheral IC chip, and its interface with 8085 microprocessor, because 8085 microprocessor, the data bus D0 to D7 are connected from here. So D0 to D7 are connected from here, and address line A0 to A7 are connected this to address and the remaining higher address. Now first of all, this is 8255. This is a chip select active low signal. If there is active low, the IC is select. So that's why first we select the proper address value for which port A, port B and CW will be selected. So now see that here 6 address are MSB and 2 address. When this is 00, then port A selected. When 01, port B selected. When 10, port C selected, and when 11, the CW is selected. Now see that what is the status of the remaining other higher bits. The status is 111. So now what is the status? FCH, then FDH, then FEH, and last one FFH. So this is the corresponding hex address for the proper port. These are the port, and CWR is the internal register, 8-bit register. Now this IO read bar, IO write bar is used for IO mapped IO technique. When you used IO mapped IO scheme, or known as peripheral mapped IO, or known as peripheral mapped IO, that is peripheral mapped IO, then you use this two control signal, that is IO read bar and IO write bar respectively. This is for read operation, this is for write operation. Okay, this reset signal is connected to the reset out for the microprocessor for resetting this 8255. That means when in a microprocessor, the resets in switch is placed, then there is a reset out active low signal is coming out. So this signal is present here, active high, active low, anyone is coming out, then the 8255 is resetted. And this is 8-bit data bus, and here this is port A, lower 4-bit, this is upper 4-bit, also port A. So now here one thing should be remembered, that when we initialize the CWR register, then it should be in our mind that port A here used as output. So now for the operation, D7 equal to 1 for simple input output, D6 D5 equal to 00 for mode 0. This is for mode 0 operation, because in a mode 0, port A, port B and port C are used as a simple input output. D4 is used as a port A, that means 0. This is port C higher, that is don't care. This is port B mode, that is 0. This is port B control, that is don't care. This is port C lower, that is don't care. So what is the status? 100, and say consider remaining all bits are also equal to 0. So now the address is 80. So this is the CWR. This is a CWR data for initialization to recognize that port is used as output. Now here we used 17447 IC. This is a common anode type, and this is known as, this 7447 is basically known as BCD to 7-segment decoder IC. It's very important because there are 9 from 0 to 9, 8 and 9. There are 10 numbers are allowed. That's it, known as BCD. So when you apply this 000 in the 7447 decoder IC, then the output of the 7-segment decoder is look like as this 0 digit, and when we apply here 1, then the output is look like this. When 2, the 2 will look like this. When 3, and should be remember this is a common anode type, and when 4, this is 5, this is 6. 6 is shown here because the internal decoder problem. We'll fix it in the another video. 7, and this is 8, and 9 is look like this. Okay, so from 0 to 9, 1 2 3 4 5 6 7 8 9 10. So 10 numbers are are shown by the 7 segment display, and these output are mentioned here. These are common, that's why this is active low output, because this is a CA type display, common anode type display. Okay, and there are basically for a common anode display, this is a segment of the 7 segment, and each segment represented by the letter A, B, C, D, E, F, G, and these are decimal dot notation. Now for A, B, C, D, E, F, G, and H, now when the input equal to 0 0 0, then it's look like this. So now these A, B, C, D, E, F, G will be off. These A and B will, this A, B, C, D, E, F, this is G, this is A, B, C, D, E, F, G. Now this is A, B, C, D, E, F, and G. This A, B, C, D, E, F, and G. Yes, right. This is A, B, C, D, E, F, and G. This is A, B, C. This is A, B, C, D, E, F, and G. And it is also A, B, C, D, E. This is F, and this is G. Okay, now when we apply the input A, B, C, D on 7447, because in a 7447 there are 4 input A, B, C, D, and there are 8 output from A, B, C, D, E, F, and last one is, yes, right, G respectively. Okay, okay. So now when this ABCD equal to 0 0, that means this segment, so now this is for A, that is A, B, C, D, E, F, all bits output are equal to 0, because this is a common anode type. E, F, not G and H. If H will be on, then this is H equal to 0, otherwise this is off. Now when this is 0 0 0 1, so for 1 only A and B are active low, the remaining bits are get 1. Okay, and for so on, the another bit pattern will be present at the 7447 output. So this is the functionality of the 7447 IC, and there are also 3 input are available, like a lamp test, RBI, BI, and blank output. These will be not discussed in this lecture. Okay, so now there is a resistance connected between the common anode display and the one resistance connected from the plus VC. That's why this is a common anode type connection. So when the active output equal to low, the corresponding display will be on, and if there is on, the corresponding display diode, that means A, B, each segment will be off. Okay, so depending on the status. So now what our logic is to glow, so transfer the data and to show the number in this. But here on thing is mentioned that in a 7447 the input BCD only allow. Okay, there is no hexadecimal code are allow, because in a 7447 only input in the input 0 to 9 are allow, the remaining bit are not allowed. Okay, so now see that what is our CWR. We see that our CWR address, CWR data is 80, and these are our different types of address lines for different number port. So now we start our code. So first, for the code, the algorithm 1 is make CWR initialize. First CWR initialize. So that's why we transfer these 80 data in a accumulator and then out to the port CWR. So this is sent to the CWR. So this is also known as CWR address line. Okay, out FF. Okay, so now what will you do that after this we transfer the data in the 7 segment, say for example MBI 00. So now this is out. What is the port address? Yes, right, FC. So now what will do that? So now the data bus content is 00. So 00 means 0000. So this 4-bit is present at port A upper, and this is port A lower. So now here present 40 and here present 40, this in this line. So now what is the output? Output is 00. So that's why this is a 7 segment, like for any other number. Say for example for any number, if their delay program is called, okay, so now MVI 01, okay, now for 01 it will be show the 1 at the port A. Now for again call, okay, so instead of this programming we use another method. What is the method? The method is MVI. Instead of this MVI instruction, we can use this is call instruction. We increment the increment instruction, increment A, okay, and after this increment A, it will say for example before this initialization, here we say MVI B09, okay. Now after this increment it compare with B, okay, that means in the register B the content is 09, yes, right. So now actually we store 0A, okay, not 09, 0A, or okay, just see that when after this compare we check the 0 flag status, because you know that this compare is executed between the accumulator present number, the accumulator and the B register. If the two number equal to 9, then the output equal to 0 flag will be set, otherwise not, okay. So when this is not equal to 0, then we again go back to, yes, right here, L1, then again out. So now instead of 9, basically we use A here, okay, because 9 will shown, because 9 will be sent at the output, okay, otherwise there is an error, otherwise this will count from 0 to 8 only. So now see that first is CW initialize, then MVI B0A, 10 numbers, MVI A comma 00, then out FC address, port A address is a port A address. Now call delay, then increment the value of A, that means A equal to 01, compare B, is it 0, compare B, no, because accumulator content is 1 and there is a, say for 10. So now using compare B, 0 flag is equal to 0, so jump if no 0 is it's a true, so that's why coming here. And when this is a 10, so now when this is 10, okay, and this B content equal to 10, so compare both the number, because in accumulator there is a content of 10 after the 10 increments, and in a register B there is also A. So when these two are compared, then 0 flag will be set and this statement is false. So now the loop is not continue, and again here we jump the another address, jump from here to here. This is MVI B comma 0A, because this is a basically counter, decimal counter from 0 to 9 will be shown here, 0 0 1 1 2 2 3 3 4 4 5 5, sorry, actually 0 1 2 3 4 5 6 7 8 9, and again come back to, yes, right, 0. So this is using the 7 segment decoder IC chips we can use this type of programming facilities, okay. This is a very important, okay. So check these in a 8085 software, okay. So now for check this code in a software, now we write this code properly, and now first of all MVI A comma 00 hexadecimal, so it's 00 not 0080, because this is a CWR status, then out FF hexadecimal, then L1 is placed here, L1 is address. Now in the L1 MVI B comma 0 A hexadecimal, right, then MVI A comma 00 hexadecimal, okay. Then here, sorry, here actually the L2 is, and then L1 is out FCH, then call delay here, then INR A, compare B, JNZ L1, JMP L2. Now for the delay programming, this is a subroutine. We know that what we will do, LXIH FFFF. So here you use small delay, basically small delay. Now DCXH, move A comma L or H, and check jump if no 0. This is L4. If this is no 0, we come back again here, L4. Okay, and after this return from this subroutine. So see that here accumulator content is basically changed. So now in our accumulator there is a problematic when the call instruction executed. So what we can do, our task is basically that when this increment A is possible, because after this call the accumulator content again equal to 0 0. So that is problematic for us. Okay, so now what we can do, so our task is basically change here some code, because when the delay program is called the accumulator content is changed. So that's why we change here the logic. I will do okay, first of all, one here we use the another register says C. Okay, so now then it's transferred to the accumulator and then out FC. Okay, is it okay? So now when compare is now after this call delay, this increment will be not possible, because after this call delay program, okay, the accumulator content is basically changed. So now what we can do, our task is okay, now see that we use some logic here, some changes. We instead of INR, we here use increment C, because C value is not get altered during this programming, and then C value, the increment value is transferred to accumulator, and then check it with B, because B content is 0. Okay, if it is not equal to 0, then jump. If no 0, then this is jump again here, because out FC the last value is the last value of increment value of C is transferred to the A. So now then again, and then call, and if accumulator is content is altered, then there is no problem, because this increment C and then transfer to A, and then compare B, and then again. And if there is the compare is successful, then this loop is fails, and again jump back to this here. Okay, now consider I think this is okay. Now check it. Now first of all, for here we use one peripheral device mapping. So now this is the input output port, this is output port. So what is the address of this port? The address of this port is basically, yes, here FC is used. We use FC here because this is a port A address. So now see that all LEDs status, during the LED status will show that how programming will be done. So now this is step by step. First of all, oh yes, sorry, this first assemble and load first. Okay, there is no error. Then start and step by step simulation. See that it is now, this is jump in the subroutine. Now see that in the accumulator there is a B. Okay, now see that the accumulator is changed because the new value initialized in the accumulator in this delay subroutine program. So now see that what is the status. So now again come back to this. Now see that the LED will be glowed. Okay, because in this simulator ID the 7 segment display is not available. So that's why I use the LED status, because this 4 LED represent the higher bit of port A4 to port A7. That means this port, this 4 port, and port A0 to port A3 is display this 4 port by this lower 4 LED bit. Okay, now this is 1. Okay, now again for the step simulation we see that again it is in the delay programming. So after ending the delay program there is a timing is required. So now see that after this the value is 2. Now see that the value is 2. Okay, it's a very interesting. So now if we hit a normal, then see that this is automatically show our programming. So this is read fast. So now this is a read, there is a 2. Now see that after some time, now this is 3. Okay, if we rate much more fast, now show that this is 4, this is 5, this is 6, 7, 8, 9, and again come back to 0, 1, 2, 3, 4. Yes, right. So this is very interesting. Okay, and 9, and again come back again to 0, 1, 2, 3, 4, 5. So this is very interesting for the 7 segment display programming. Okay, so our program is okay, so there is no problem. And if you use the down counter, and if you use or to design the down counter, then you starting from the 9 and come back to again 0, and then again go to the state 9. Okay, so that's why this programming is very important for us, and just to stop the simulation, otherwise it will be running. And this is a log file generation, how many T states are required, what is a flag status, how many clock cycles are required, what are the program counter address, what is a instruction by part instruction line number, and what is a register content in a 8085. All things, stack pointer also shown in this programming. Okay, and next, what is a maximum clock frequency is used, and what is the simulation time is required for this programming. So that's why this 7 segment interfacing using 8255. Okay, that's why, because this using this 7 segment encoder, we also use the temperature controller or temperature display, or to velocity acceleration display of any of any that means automobile system also, application in automobile system also, and also used in automation. There are lots of applications. So that's why these are very important for us. That's all for today. Thank you.